with my lecture before Thanksgiving on enzymes. I thought it was a little rushed and a little math heavy and not a lot of like.
My sister enjoyed it.
Oh, okay, that's good. How did your sister watch it or something like that?
I had to pick her up from the report, so you were playing in my car.
Oh, awesome. Very good.
She sat there, I made her listen to you teach.
All right, well, so I uploaded yesterday's lecture and the other sections today on YouTube, which is a much more clear lecture. So if you guys want to go back and you want to think about this a little more, there's another opportunity. I thought I did a little better job on Mondays. But we'll continue on with it, and I want to I don't want to dig too much into the nitty-gritty of the math and kinetics. I'd rather look again at the kind of practical consequences and also physical consequences of enzymes. And I just want to look at an interesting example and see if we can learn some general principles about why enzymes are so effective at their job. And we'll go back and return to inhibitors and think a little bit about inhibitors as well. And I have a nice example from biochemistry to consider. Okay, so let's go back to where we were. I want to just do a quick recap of our Michaelis-Menten model. We will return to this model, but we won't dig in too much into it. You remember again, the idea is that we start with an enzyme and a substrate molecule that we want to react. There is a reversible association where the enzyme binds to the substrate to form an intermediate, ES. So this is our what we call our complex, the enzyme and the substrate. This process, this reversible process, again, has a rate associated forward and backwards. We call this, again, this is the binding step of the system. Binding turns out to be very interesting. Some things just kind of snap into place. Some enzymes reorganize their structure dramatically as a substrate comes in. Sometimes you need multiple substrates. Some enzymes can take multiple substrates at a time. Right? Lots of different opportunities. We're just going to keep it simple. Right? Some binding process. And then again, once it's bind, this complex is what does the work for us. And it catalyzes the reaction at some rate kcat to give us the product. And the enzyme returned ready for the next substrate to arrive. Right, and we showed that if we let this Km be an equilibrium constant, which we call the binding efficacy, or the binding constant, depends on who you talk to. You talk to a chemist or a pharmacologist, and that's equal to the concentration of the complex divided by the concentration of the enzyme, divided by the concentration of the substrate. And of course, this has, of course, a delta G associated with it. This is an equilibrium constant. Right? It's E to the minus delta G binding, whatever the Gibbs energy of binding is, over RT. Right? And we can also, as I showed you guys last time, this is also equal to the ratio of the forward to the reverse rate. Right? There's lots of different ways we can think about equilibrium. We can think about it in terms of delta G. We can think in terms of rates. Doesn't matter. Okay, so the idea is that we want a really, really effective enzyme. We want this number to be as small as possible. Why do we want it to be as small as possible? Well, that means that we have the most. This needs to be a positive. Excuse me. Be a positive. Have it flipped. Is that right? If delta G is really negative, positive. It's going to be really small. Yeah, it's going to be positive. We want this to be as small as possible, right? Because what we want is for our enzyme to be completely bound with as little substrate as possible. So ideally, we want this to be a really small number. Do I have that flipped? No, I don't have that flipped. Right? The lower km, the less S we need. To generate the macroscopic amount of our complex. Right, the idea is that imagine that we want to generate a mole of products, right? That means that at some point we need to generate a mole of complex over time. And if this number is large, right, if this number is large, that means we have to feed in a large amount of S, all right, a significant amount of S in order to get the enzyme to bind to enough to have a mole of our complex and create a mole of products. So the less this is, right, what it basically means is that when S's are floating around the enzymes, substrates are floating around and they come together and they meet. If Km is really small, that means the probability of binding is really large. Same idea if you have an effective drug, you only take a small amount. If you have an ineffective drug, you're taking horse pills. Same idea, S needs, for Km being large, S needs to be large to have some sort of action that you want. Some threshold level of function. So Km is an important number. It tells you how effective the enzyme is at binding, which is only half the story. The enzyme also has to do some work, right? So it has to catalyze our reaction as well. And the equation that we came up with at the end of our earlier on in the class is that the rate of formation of the product, P, which we call the velocity, V, is equal to Kcat times the initial concentration of the enzyme, how much enzyme you have in your body to begin with, or your system, times the load of your substrate, right? How much substrate you load into your body, divided by Km plus the concentration of S. So the formation of our product depends on, right, the more enzyme we have or the more substrate we have, it's up to some limit. The more enzyme we have, the faster it reacts. Or just like we said with Walmart, the more registers you have open, the more customers you can process. The purchase rate increases. Of course, if you have a sufficient amount of you have more enzyme than substrate, then as you increase the substrate, you start to fill the registers. So more than happy to rate increases of product formation as you increase S, but only to some limit. Eventually, if you have too much S, if S is very large, then you've just got, then your enzymes they're all waiting for the enzyme. Right? So we can kind of look at that. If we take S to be very large, right? We've nuked our body with a large amount of drug. This Km is basically a negligible number, and the S dependence cancels out, and we're left with Kcat E naught, right? Which is the fastest the system can react. This is the rate of when you have all your enzymes and they're all ready to tackle to go. Right? This is the fastest it can go. We call this Vmax. This is, so technically there is some limit to the rate of enzyme catalysis, and that's the rate at which all the enzymes are occupied doing the same job and there's no one waiting for it and they're just pumping through them as fast as possible. All right, but there's another limit, right, which is where Km is large, right? That's poor binding, right? If we have a system where Km is large, right, this is poor binding. Then we can say that we can neglect the S here. We have E naught S over Km. You can see that when we bring Km here, we're going to have an S. There's going to be some cancellations. So let's see what that looks like. We have E naught, and cat, S over Km. Right, we're neglecting that S in the denominator, it's small. Km is ESE over S, ESES. So once we get that in, we have the function would be E naught over E times K cat times S squared. Right, so now what happens is when Km is really, when the system is really poorly binding, when the protein doesn't really feel that interested in binding to the substrate, now the kinetics are dependent on two molecules of substrate, right? You forces the system to drive your substrate concentration up. If you want a specific formation rate, you've got two factors of S you have to deal with. If it requires more substrate, it's begging for more substrate. Right? And that's just Le Chatillier's principle, right? If you have a system that is reactant favored, the only way to make more products is to jam more reactants, right? Push all their equilibrium towards the reactants, it's going to drive things towards the products. And that's what this is saying, right? You need to increase your S, right? So reaction is limited. Reaction rate is limited by the concentration of your substrate. So we have two limits, right? We have the reaction limited by the substrate concentration, and when S is large, the reaction is limited by the catalyst, by the enzyme. Yeah, not so complicated. The math is a little funky, but exactly the expectation that you would have physically if you have a bunch of enzymes in a line. I mean, they're feeding molecules into it in like a factory. This is about a balance of labor for productivity. Okay. So what I want to look at today is I want to look a little more detail at how and why enzymes are so effective at what they do. Right? And enzymes in particular are extremely effective at what they do. We talked a little bit about it. I want to show you a table that I found in a book of mine, not a book I wrote, but rather a book that I own, that really blew my mind. And the answer I want to talk about today, I mean, we'll come back to inhibitors. That was one of the things we talked about, and we'll talk about it in context. But one thing I want to answer today is why are enzymes so effective? Why do they work so well? They are, as I've said before, they are convergently evolving and divergently evolving objects that have been designed either by entropy or whatever you want to say. Certainly by entropy in time, selective evolution, to be very finely targeted towards specific operations and doing it really, really well. Extremely well. Better than any man-made chemistry. And I want to show you a really surprising graph, not graph, but rather table that I found in a book about how effective these enzymes actually are at the chemistry that they perform. So I think it's on page, yeah, right here. So this is a plot. This is a table of a selection of enzymes. That we'll talk a little bit about what each enzyme does, or kind of generally, and comparing the rate of the reactions that they do with the enzyme present versus the enzyme not being present. Every reaction the body does effectively, there are some exceptions, but the basic chemistry that the body does is just basic organic chemistry. It's hydrolyzing things, it's creating bonds, it's adding acetyl groups to things, just organic chemistry reactions. And so you can imagine this reaction that your body wants to do. And you do it either with an enzyme or you just do it in solution. Right? And we'll think about what the enzyme is doing, and maybe we can replace it with some other chemical reagent. So for instance, in hydrolysis, if we have a molecule or an enzyme that hydrolyzes a molecule, we can simulate that by just using acidic or basic conditions, by just applying some basic or acid. And to think about how fast does it happen in solution versus how fast does it happen when you have an enzyme. And the numbers are dramatic. So here's a selection of enzymes. And this is the ratio of their rate catalyzed versus uncatalyzed. So there's a series of different reactions. We can look at them if we like. But anyway, the rate enhancement ranges from anywhere from a factor of 10 to the 5. That's a factor of 10,000. Sorry, 100,000. 100,000 times faster, 10 to the 17. Right? That's 720 quadrillion times faster. Right? So basically, right, what does that mean? Well, imagine, let's just say, for instance, right, that the uncatalyzed reaction is around 10 to the minus 6 per second per molar. All right. So that means it takes with normal conditions, at normal conditions. So at a concentration at 298 Kelvin and a standard concentration of our reactants of 1 molar. This means it takes about 10 to the 6 seconds to generate 1 mole of product. Okay, of course, that's not really fair because nothing's at a concentration of 1 mole in the body. Things are much more dilute. Some things are much more concentrated in the body. But most proteins are not at 1 molar concentration. They're at millimolar or micromolar scale. We have to do a little bit of unit conversion. But just as a comparison, let's say roughly it takes 1,000,000 seconds, right? 1,000,000 seconds is, I'm just going to quickly calculate it, because of course it's kind of hard to think what 1,000,000 seconds is. 60 times 60. So that's an hours, 24 hours. It's 11 hours. Is that right? 60 seconds, 60 minutes. Yeah. Sorry, 11 days. It takes 11 days. All right. But if we put a catalyst in there, it goes 10 to the 17 times faster. Right? So that means that Kcat is 7.2 times 10 to the 11 seconds per second per molar. Right? What does that mean? Well, that means that to generate 1 mole of product, let me get the number exactly. To get 1 mole of products, it takes 1.38 times 10 to the minus 12 seconds to generate 1 mole. Right? You've taken a reaction that takes a macroscopic amount of time, general conditions, and now you've put in a situation where the effective reaction time is a blink of an eye. It's faster than a blink of an eye. Right? As we'll see that this is basically instantaneous, as we'll see in a second. In a protein, this is basically as fast as possible. So enzymes are really powerful. They take organic reactions that, as we'll see, at normal conditions, are completely so slow that they don't happen. And then when you bring in an enzyme in, they become so fast that they happen in a blink. There are no man-made catalysts with this kind of rate engagement, just period. There might be an exception, but I don't know. And I think I've mentioned before, if I didn't, maybe it was the other class. But there's a whole field of people that study catalysis, where they do what's called biomimetic catalysis. They come up with things that look like enzymes to take advantage of the natural enhancements of enzymes, but to tune the structure of these enzymes to more suit their goal. And there's a whole biochemical process and where you can get the antibodies to express these enzymes through monoclonal antibodies and other types of engineering, genetic engineering. You can make these enzymes to do something for you. And what people typically find is that they work, and they work fairly well, but they don't work as well as the real thing. The enzymes that have been developed over millennia and eons and generations of living things have been evolved so perfectly that there really isn't anything better. And you'll see that this is the limit. In some sense, they can't go any faster. What I want to look at in particular, if you look at these different enzymes, they all have different names, and enzymes are named after the thing that they do. So the top one, the fastest one, is the sweet potato beta amylase. That's an enzyme that does a specific cleaving function in the sweet potato. And in particular, if you ever see an enzyme that ends with ACE, ACE, you'll see these all end with ACE, ASE. These are a specific class of enzymes. These cause a cleaving. These do a bond cleavage. They break molecules down. They're recyclers. They might also do other things, but oh, I'm sorry, I kicked it off. So these are enzymes that take a molecule and break it into smaller parts. Right? But enzymes are really, really good at doing this. And of course, your body, every secretion, every object, every liquid in your body has these enzymes in them because it's what breaks down food and bacteria and any other sort of organic matter that you want to get rid of. So it's all sorts of different ones, and we'll look at an example today at one of these ACEs. These what are called proteases. Yeah, so this is, let me write that. So these are called proteases. When I was younger, I thought they were proteases, but they're proteases. Okay. So I want to explore kind of physically why these are so good at what they do. Right, and I want to look at a particular protease that's in the pancreas, part of your GI tract. Then your pancreas develops this protease that is in your duodenum, top of your small intestine, and it's an essential part of the juices that break down your food. In fact, it's what breaks down proteins. So I want to look at an example, and let's just try to explore chemically why this enzyme works as well as it does at what it does. And first, we need to think a little bit about what the reaction this enzyme does. So the one I want to look at is what's called chymotrypsin. This is an enzyme secreted by, as I said, enzyme found in the duodenum that breaks down proteins. Right, and there's a big long series of proteases. Every living being has a class of proteases that do different jobs. Chymotrypsin is one of the proteases. And it has a very particular function. Chymotrypsin only cuts one type of bond. It's extremely effective at cleaving one type, all right, that's supposed to be TYPE, a peptide bond. It only does one thing, and it's between, it cleaves to a polypeptide. It could be like, a piece of something that's in your food. could be a bacteria, could be a cell, anything like that. At the nitrogen terminus of an acid of an amino acid sitting next to a very specific type of amino acid, another amino acid with a side chain that is large and hydrophobic. I'll draw a picture of this so you guys can see this. Again, I'm assuming a little bit about if you guys don't understand what an amino acid is, but let me draw it. So let me show you an example. Right. So for instance, maybe we have we have some peptide, something that's come from our food. So we've got this molecule. It's got a bunch of amino acids on it. It's some protein. And then let me draw. So then we get our first chain. Maybe this one is an alanine. Doesn't really matter what it is. Hold on a second. Let me get this right. Yeah. And then, so this is alanine, this first one. Am I missing options? So this is alanine here. That's alanine, and it's connected to something with a big fat functional group on it. So we'll put like a tyrosine there. So that's going to look like, I just want to get the drawing right here. So a tyrosine has a CH2 group and then a benzene. This isn't tyrosine, excuse me. This is phenylalanine. And then it continues on. Phenylalanine. And what this does, what this system does, what trypsin does, is it comes in. Trypsin comes in and cleaves this bond right here. Trypsin says, and it cuts this bond into two. And what it's going to do is it's going to make this an amine, and an NH2 on this side, and then you're going to get a carboxylic acid on this side.
Sorry, I have a
Go ahead.
So the yellow line on the very far right, that should be before
And
the
this should be after.
nitrogen, right?
Yeah.
Which
So yeah, so I gotta be careful, right? So we'll assume that this NH is the NH terminus of the alanine, and then I'm sorry. So then,
well, that one would be correct. It'd be the one on the other side that would be off.
so it's this one.
Well, then alanine then would have two nitrogens on the side.
Oh, right. So I've actually, yeah, sorry,
The
yeah. So
phenylalanine
I need
is
I need to cut this here, and then cut it here.
There we go. Yeah.
So the trypsin is going to cut here. It's going to put in what's going to happen here is it's going to put an OH group here, and it's going to complete the. Actually, no, it cuts it differently. Actually, sorry, it cuts. So this is the break between the two. It actually doesn't cut there. It cuts here. On the left side, it's going to make an NH2 over here, and it's going to put an OH here. All right, so let me show you the mechanism of that. It's going to cut basically it's going to cleave this amino acid in half. You're going to have an NH2 on one side and an OH on the other side. And carboxylic acid on one and an amine on the other side. Hence the name amino acid. All right, well, let's just roughly look at this structure. and think about a little bit about what has to happen for this to occur.
Chymotrypsin usually cuts after aromatic rings rather than on. Oh, yeah, that's
right,
exactly,
right?
Yeah.
Yeah, got it. So what we want to do is we want to cleave this bond right here. Right. So how are we going to do that? Well, there's a couple of steps that we need. Right. One thing is that we're going to have to displace this amide group to this oxygen and replace it with a carboxylic acid. Right. So we know that somewhere along the line, an OH is going to come in here and eventually kick that NH off. Right. Nucleophilic attack at the electrophilic position at the carbon. But here's the problem. This is a terrible leaving group. This is a strong base. The amine is a strong base. So what you're doing is your leaving group here is going to look something like an NH2. We're going to have to add another hydrogen in there. That's another thing. It needs to have 3 bonds. Ideally, it's going to be NH2. This is a strong bond, a strong base. And these make poor leaving groups. So cleaving that NH bond, this bond right here, is actually really, really difficult. Right? So what do we need to do? We need to make this easier to fall apart. Okay? So what we need to do is to use the fact that this is basic, right, and have it perform an acid-base reaction on water. What is that going to do? Well, if I draw my carbonyl, now I'm going to have NH2 here. This nitrogen has 3 bonds now, and so it has a plus charge. There's 4 bonds now. All right. I'm just going to kind of draw the rest. Bless you. And so that's a much more effective lead, right? Because I can come in here and this NH2 wants to remove one of those bonds anyway, and this thing's going to fall, right? This is going to be very nice, right? So we can do something. We could take that OH, come here, kick here, and kick this off, right? And now we get a carboxylic acid and an amine. So that's great. Right? So we have some idea, at least in solution, about what needs to happen. We need a nucleophile. We could use OH for. We need an acid to protonate our NH, right? This is the pKa needs to be low enough that this becomes protonated. You see a problem? We need a base and an acid. Right? We need some sort of nucleophile, which is typically basic, but we also need an acid to protonate, because amino acids are zwitterionic. They have an acidic end and a basic end. They're both electron donors and electron acceptors. They're both Lewis acid and Lewis bases. The carboxylic acid is a Lewis acid. The amine is a Lewis base. And so the problem here is that in order for this reaction to be facilitated, you either need to be a really low pKa or really high pKa. Right? So this is only effective. It turns out you can also grab it from here. I could do it like this instead. Right? You could also do this. So this needs acid, right? Needs acidic conditions. What's the problem with that in the body? We don't have acidic conditions in the body. The pKa of human body is about 6.8. There's no acid in the body. It's very weakly acidic, if at all. So this reaction is a no-go in biochemical environments because we're not in acidic environments. Our cells can't survive the environments required to do this hydrolysis, or this peptidase, as it's called. Right, so that's no go. Right, unless you're the alien from Aliens, because it has acid blood. More than happy to do this without an enzyme, but we're not going to have that luxury. Okay, but imagine now that you have this protein, you have this really, really long protein that you've ingested, and you've got to break it down because you have to excrete it at some point. Your body isn't going to break down some long 200 amino acid chain. It just can't. It has to break it down into smaller parts, which then can be broken down further. And eventually, right, that whole thing is going to come back into your Krebs cycle and your electron transfer chain and generate energy for your body. Your body can't take a long peptide and do something. It's got to break it down into smaller parts. So your body has to facilitate this reaction somehow, but it has to do it from a perspective that is neutral. Well, pH, basically neutral pH. And the way that chymotrypsin does it is brilliant. Really, really simple. How much time we got? Good, plenty of time. So let's look at the chymotrypsin environment, about where it actually takes this molecule and does its work. And we'll look at a picture of chymotrypsin in a little bit. Right, so the key is that we need an acid. Maybe we need a base, but we certainly need a nucleophile, right? So we certainly, right, the goals are we need for effective reactions, we need acidic an acid proton, a conjugate base, right, and a nucleophile. Those are the three ingredients we need for effective cleaving. Or peptidase action. Peptidase means cleaving peptides. Peptidase action. Right, so how does chymotrypsin facilitate all of those goals at once? Well, let me show you a picture of chymotrypsin. This is chymotrypsin. Let's see if I can find one with a complex. Actually, I can show you it without something. Yeah, this is a nice picture of one. So this is one of the chymotrypsins. This comes from Bos taurus. That's a cow, I think. This is the crystal structure of the chymotrypsin, and it's been complexed. It's complex that chymotrypsin with its own autolysis products. So what this is chymotrypsin with some of the leftover material stuck in it. Let's look at the structure in 3 dimensions. Let's see if I can find the molecule. Yeah, so here's a molecule here. All right, so this is the leftovers of one of the substrates. Right, it's already cleaved it. And I don't know where the other cleaving component is, but it has a tryptophan in it. This is tryptophan. This is the tryptophan side chain. It's a large aromatic side chain, no tryptophan. And this is the amino terminus that's been cleaved. And there should be a CO terminus somewhere on this side as well. Okay, so this is the leftovers of the process. One of the components has left, and there's just left with here, right? And what do we see? Well, it's kind of hard to tell. So these ribbons here, this is an alpha helix. This is a helical structure, the ribbon structure of the protein. Each one of these, there's little components here. Each one is a different amino acid. And in fact, you can see one of them, the amino acid components here. There's this tryptophan right here sticking out. This is on this chain. And one of the things that's really you can kind of see from this picture is that this tryptophan, this big clunky planar material, is like stuck inside of this pocket. You can kind of see it's the deepest thing in the complex. I'll try to zoom out a bit. You can see it. Right. Here's that tryptophan, right? It's buried deep in this pocket here. Right, this pocket in particular is a unique component of these trypsins. And so you can see the amino acids kind of looping around here on the pocket. And it turns out that the choice of the amino acids in this pocket actually determine which molecule goes in there. So there's a special pocket for tryptophan, there's a special pocket for phenylalanine, there's a special pocket for threonine, some of the other larger complexes. And so each of the trypsins in particular have this unique pocket that is designed in a specific way to accept this hydrophobic residue and to bind it. Right? So there's some other non-polar objects in there that give you dispersive and pi interactions. We've talked about those before. To bring this in and lock it into place. It's not doing any chemistry here, but it's providing a locking mechanism to hold the molecule into place so the rest of the protein can do its job. Right? This is true binding. Right? This is a binding pocket, as we call it. So let's go ahead and draw that, right? So you have your protein here. So this is your protein binding pocket. Right? And our tryptophan or our benzene or whatever it is, or phenylalanine, we'll just do phenylalanine, sits inside of this little pocket, right? And the protein can, do all sorts of different things and so on and so forth. It doesn't really matter here. Continues on. The tryptophan or phenylalanine. And the system continues on. So it sits in there. Right? And there's going to be another protein or another amino acid on this, which is the one that's going to leave it. So here's our alanine. And of course, this continues on. Right? And the system is going to cleave here. So what's happened is that we have these nice dispersive interactions between this pocket. I don't remember exactly. I think there's an aspartic acid in here and stuff, but there's different pocket residues, different amino acids that lock in. Right? So we get some binding through intermolecular interactions. And that locks the molecule into place. Right, and the protein loops back around. Let's go back and look. And if we look at the perspective of the molecule, sorry, position. Right, these loops. Right, there's some other loops looping around on the outside of the molecule. There's a loop of the alpha helix here. On some unorganized amino acids on this long strand right here. So there's a bunch of tendrils, all kind of looped around the molecule with this primary tryptophan residue that I'm showing here stuck in this deep pocket. So somewhere else on the molecule, the protein literally folds around it in such a way, going to bring the molecule in, that there are some nearby residues that will be useful for you. One of them in particular is a serine. That's a SER, serine. The serine functional group is an OH. Oh, sorry, it's a CH2OH. I forgot, forgive me. CH2OH like this. Serine there. And then somewhere over a little further away, there's a histidine. And the histidine has a aromatic molecule as its side chain. Histidine here. And then further down the line, there's an aspartic acid. This is histidine. All right, let me write. In case you guys don't know these names, that's okay. There's an aspartic acid. It's the other one. And aspartic acid just has a acetic acid. Okay, so on this protein, they're not connected to each other necessarily. They're like little tendrils off the protein that are all in this binding pocket. This whole thing we can call kind of this region. This is all the close region around the molecule. This is that binding pocket, right? It's when I was drawing those little Pac-Man diagrams last class, these are the little openings in the pack, little pockets. And these three right here, provide us the three ingredients that we want. Here's our nucleophile. Here's our acid, here's our base, conjugate base, and here's our acid, aspartic acid. So there are the three ingredients all sitting here, all waiting in the same area in this little pocket, and each one of these residues that bind to the molecule function as one of these options. So I can just draw some arrows for you. How does this work? The aspartate is going to take this hydrogen off the ammonia, right? And that's going to push the electrons towards this nitrogen on the other side of the histidine, right? So now you have a buildup of electrons on the histidine. It wants to donate those electrons as a donor. That means it's a base. And it's going to take, let me spread this out, this H here. It's going to attack this H. That's going to push electrons towards that oxygen, making that oxygen more negative. And then oxygen needs to get rid of those electrons, and it's going to function as a nucleophile and attack here. Right? So we have an acid-base reaction, a Bronsted-Lowry acid-base reaction here, and then a Lewis acid-base reaction, and then a nucleophilic attack, all in one concerted step. Right? And what does that do? Well, as you can see now, we're going to leave this bond. Right, but we're missing one step, right? We still don't have another hydrogen here on this ammonia. Right, so what does our intermediate look like? Here's our phenylalanine. And then O minus here. Let me clean this up a little bit. O minus here. Minus here. This is the serine. This in H. And this goes to our algae. Right, so what we form now is a tetrahedral intermediate. This nucleophilic attack, we form a tetrahedral intermediate here where the serine is now, in some sense, connected to the substrate. And all we need now is another water molecule to come in and to give us a proton. So another water molecule, we can imagine there's some water molecules in the system. Of course it is because we're in the body. The water molecule in here, this nitrogen is going to attack it. take that hydrogen to form NH2 plus. Right? And now we can regenerate the molecule, right? We now take this and then break this. Oh, sorry, that's not right. Break this. Now what we have is NH. So phenylalanine. We restore this double bond. And now we have an O- atom here, which is that OH that's left from the serine. And we have NH2 alanine. So we've cleaved that bond now. And all we did was put it in an arrangement, right? We locked this molecule in with its little hydrophobic pocket. And then there are 3 reversible steps that all happen in a concerted fashion between aspartic acid and serine to provide the acid, the conjugate base, and the nucleophile. And the whole thing goes and reacts and cleaves our molecules to the final step. Now, you might recognize that I'm missing some O's and some H's here because of all the different things here, but you can imagine that it waters around and they all recover. The system returns to some standard state with some acid-base chemistry. All right, so here's the cool thing. The structure of this binding pocket determines what amino acid fits in there. Okay, so not surprisingly, there is a very, very, very long list of peptidases, trypsins, that all kind of look the same. But what happens is that maybe one of the residues, one of the amino acids in a binding pocket changes, and that changes the interactions enough that another amino acid from a substrate comes into there. We have phenylalanine or a tyrosine or a tryptophan or whatever. So small little changes in the binding pocket that change which part of a peptide comes in here and locks it in place. But what doesn't change amongst all of them is this 3.
Is that like an example of the induced fit method?
Yes. Well, sort of. Let me come back to that question. So one thing that doesn't change amongst the peptidases in particular is the serine histidine aspartic acid combo is conserved amongst nearly all forms, all classes of proteases. Every single one of them almost has in their binding pocket. There's some exceptions, but let's say 90% of them have serine, histidine, and aspartic acid. And they all do all the work. There's a term for this, the biochemists has called it. This is what's called the catalytic triad. And this is the amazing thing, right? Is that the body, this is why the amino acids are so powerful, is that each of them in context performs a duty. Now, some amino acids don't perform chemical duties. Some do, right? There are 3 that do very discrete chemical duties. There are some that are floating around. Most of them float around, don't do jack shit. But they do something that is important. Right? So you can go and look through all the proteases. You always see the serine, histidine, and aspartic acid. But again, we go back to this protein structure. I'm just going to go back a page. Right? This protein has 241 amino acids. And I just explained that maybe 5 of them are important for the reaction. Right? So why the hell do we have the rest of them? Well, the point of the rest of the protein, of the rest of the amino acids, right, the rest of the structure is just to set the system up in the protein in such a way that the binding pocket forms in the right shape. The rest of the protein structure is just there as a supportive structure to ensure that the energetics of the protein folding is such that it folds into a situation that optimizes its productivity.
So is that a intermolecular interaction where it like is it electrostatic?
Yes,
where it
absolutely, absolutely.
folds out?
Let's look at some examples of that, right? So there's two kind of motifs in these systems, and only one of them is really being shown here. Well, there's a couple. There's these alpha helices, these purple things. And let me see if I can find a nice picture of an alpha helix. It's a certain sequence of amino acids that repeats.
And then they have those type of interactions.
And they
that
have
make
those
it
type of
better.
interactions that lock them into place. That's correct.
Okay.
I wish I remembered them off the top of my head. Again, as I said, I'm not the best chemist. I'm not the best biochemist in the world. It's not that great. Right. But the idea is that you have this. And so actually what happens is that on an alpha helix there are polypeptides or sugars on the outside, and they're all locked together, kind of hold them into place like a backbone. But you have a certain sequence of amino acids. I wish you told me which ones they were. I forget.
I have it written down.
Well, anyway, so the idea is that you get intermolecular interactions between the H's and the N's between the strands like this. So you have this linkage of hydrogen bonds. As it folds, it forms these hydrogen bonds between each other. It locks it in place. It's a certain sequence. There's another type called a beta sheet as well, another really common that does a similar structure as well. There's like I want one that just shows like all the side chains and stuff. A certain sequence of you can set up a certain sequence of amino acids as well, so that you can have these sequences that have loops, and you have these planar, coplanar hydrogen bonds between the NGO, and you make these flat sheets called beta sheets. And that's a certain, again, another certain sequence of amino acids that guarantees that. And so you see these repeated motifs over and over again in every protein. And so almost every protein has beta sheets and alpha helixes. Some of them have many of them, some of them have very few. But the point of all of those turns and those twists, they have, in terms of the function of this protein as a catalyst, have, in some sense, no direct influence. The only things that matter for the catalyst, the catalytic action, is the serine, the histidine, the aspartic acid, and whatever binding motif you have for the hydrophobic pocket. There might be a couple other hydrogen bonds in there as well, but these are the only things that do the job out of the hundreds and hundreds of things. The rest of them are there to build a structure, to construct a framework, a scaffold that gives you this binding pocket that fits this molecule in the way that you want it to. It's only there to drive thermodynamics towards an effective catalyst, which might only need 4 or 5 of the residues to actually do its work. But if you were to make a chain of serine, histidine, and aspartic acid that add some hydrocarbons and then make a little pocket here, make a little, like, imagine you cut this out of the protein and just keep that, it doesn't work. It doesn't fold into the structure you want. It doesn't do any of the activity that you want. But the rest of the chain exists. The rest of the primary structure or the secondary structure of the protein exists solely to stabilize that binding pocket, which has been convergently evolved or divergently evolved to specifically target this amino acid bond between a phenylalanine and some other molecule. It's supposed to be as general as possible. It's completely targeted. So proteins can be very overwhelming because they just have so many atoms and so many molecules and so many structural features. But in the end, most of the hard work is only done by a few residues. Because in the end, all you need to do is organic chemistry. You need to transfer some protons, you need to transfer a nucleophile, maybe an electrophile. You break something, you need to add something. Usually doesn't require much. So the rest of the structure is just there to support it. Okay. So I'll finish up with one more interesting note that allow us to kind of come into Thursday. So hopefully I've convinced you with this example that proteins are effective, enzymes are effective at doing their job and effective at catalyzing. And chemically, we kind of get a sense why. I mean, the system is literally designed structurally to perform a very specific task. But I want to know if I want to understand why it's so effective and why it's so efficient in particular. And is there something we can learn from the way that enzymes develop themselves structurally that we can take advantage of the things that they do? Are there some kinds of universal kinetic concepts that enzymes are very, very good at taking advantage of that maybe we don't? And maybe we can tune our reactions to take advantage of these ideas that enzymes are really good at that we may not be that. You're looking at a really great example of one in your homework, right? In the homework, you're taking a molecule which is achiral. You have an enantiomeric mix of R and S on a homework, and you're applying a catalyst to it and making the products chiral. You're taking an achiral mixture and turning it into a chiral mixture. That requires the catalyst to provide that chirality, to make S preferred over R, vice versa. And there's something to be learned about that. And you'll find as you explore that problem set that the properties of that reaction aren't exactly what you expected. And I want to see if we can learn some techniques and some ideas, some concepts from enzymes in particular, really, really effective enzyme or catalysts, if we can learn a few things about how they do their work. We might not be able to reproduce the chemistry or the complexity of their structures, but maybe there's some trends, right? There's some ideas that, energetic ideas that proteins take natural advantage of that maybe. And that's going to lead me into a conversation that will lead into next class. But let me just introduce this really simple concept. And this turns out to play an important role, and why, in particular, the enzyme is so much more effective at doing this task than it is in solution. Right? Let me show you an example of something. Drive this point home. All right, here's a common step of aspirin metabolism. Right, you take a little bit of aspirin. Right. So this is aspirin. All right, let me draw this better. Get me for my poor drawing skills. I'm going to draw this up instead. There we go. All right, this is aspirin. And one thing that aspirin does very effectively is that when you put it in water, which is a little bit acidic, it falls apart. Very, very rapid. Falls apart, especially the acid. And it falls apart in a very interesting way. You have some water here. This carboxylate attacks the water, right, to reform the conjugated acid, which kicks off this hydrogen. Oh, sorry, no, which it does not. Right, that drives electrons into the oxygen, and then that oxygen acts as a nucleophile and attacks the group here. Right, we can run through this math and do some acid base and just carbonyl chemistry, but I'll just show you the result. The result of what you get, this is what your body does to metabolize. One of the first things it does to metabolize aspirin is to cleave this and hydrolyze it. And you get an OH here. So we kick off this carbonyl, this acyl group here, and then we make acetic acid. This aspirin, this is a non-polar molecule. Non-polar, oh, it's mildly polar. Oh, I shouldn't say that. Slightly polar molecule. It's non-protic. Which means it's effective at moving through the blood-brain barrier. It's good for our painkiller. And the products are both highly soluble, highly water soluble, and polar. And the one thing your body loves to do with highly water soluble and polar molecules is you pee them out. They get excreted as salts. And so this is how your body breaks down aspirin. You get your aspirin and then it hydrolyzes it to this all this benzoyl acid, phenol out, and acetic acid, and these things just come out of your bloodstream into your urine. Okay. So here's an interesting note. At pKa of 7 and pKa of 3.7, which is the pKa of aspirin, you go look at the rate of this in a body versus uncatalyzed. And in the body, it happens 100 times faster. Okay, so it's 100x faster with an enzyme. At pKa equals 7, remember that pKa 3.7 is acidic. Right, so we could probably think that this is probably hydronium ion, right, which makes this much more effective. At pKa equals 7, right, body conditions, body pH, Kcat or K uncat is 5,000. Now, here's the interesting thing about this reaction. This reaction did not undergo any sort of interaction with another molecule. It exchanged some protons with solvents, right? But I could easily, right? Another way I could write this is to write this in its acidic form, its conjugate acid. Like this. Maybe I want to make this, yeah, OH. Right? And this can act as a nucleophile. We get an H here from protonation, and this gets kicked off. Sorry, that's not it. Okay, and we make our molecule, right? So this is an intramolecular reaction where aspirin itself reacts with itself to hydrolyze itself. Right? And the water just acts as a proton stream. All right, so this is quite interesting. If I do the same reaction now, but instead of, this must be a C. If I do the same reaction, this is a C. Oh, C. But instead of having the carboxylic acid on the molecule, I bring it in as an external molecule, where we have some carboxylic acid floating around. We have OH, and that acts as a nucleophile to then form phenol. Plus an ester. So that's what we would get from that reaction. It's exactly the same as above, but I'm using a different carboxylic acid instead, and ask the same question. Right, what is K at pKa equals 7? And ask the same question. How fast is this reaction in the catalyzed form in the body? We have a separate acid versus uncatalyzed. People have studied this. Usually about 10 to the 12. Orders and orders of magnitude slower. Impossibly slow without a catalyst. Without acid. But the intramolecular, right, which is the aspirin condition, right, where the reaction happens within the molecule, intramolecular reaction is much faster. Not only much faster, but the catalytic action is slower than it is in the other case. Right, compared to this. Right, so you need a catalyst for the intermolecular reaction with two molecules, but you don't necessarily need a catalyst for the intramolecular. Though the catalyst certainly does help. So we'll hold off that now. Now we have an interesting point, right? Now we have some process that an enzyme can provide, and the enzyme does an okay job of aspirin compared to not having our enzyme. Certainly improved it, but not by much. But now when we have a system that's being hydrolyzed in the same way, but with a separate carboxylic acid, an additional molecule, the catalyst you absolutely need. It doesn't go without the enzyme. This is only possible with enzymes. So this would mean that this is only enzymes can break this down. So the question I want to leave us with, because now we're at 4:45, is why is this? Why is it that an intramolecular reaction, where the molecule kind of falls apart on its own, I mean, helped along the catalyst, but not a significant improvement. But the moment you bring it, you separate the two substrates, the substrate into two parts, they have it do the same chemistry. The catalyst is absolutely necessary. Doesn't go otherwise at biological conditions. That would be good if you took this molecule in your body and you didn't have enzyme to break it down, it's going to slowly poison you. Unless you can pee it out or something, I don't know. But you absolutely need an enzyme to break it down. The solution to this is extremely subtle, but it has to do with entropy. Question, of course, is now that we have to do, what do we really physically, thermodynamically have to pack into that binding pocket to facilitate either of these reactions? And what is the entropy difference between the two? Is one more entropically favorable than the other? Right? One thing to think about is that we have 1 mole of reactants here. Molecules reacting with itself. And here we have 2 moles of 2 different molecules reacting with each other. We have twice as many molecules in our reactants here as we do here. 2 mole equivalent versus 1 mole equivalent. Obviously, it's going to be an entropy difference too. But why do we get orders and orders and orders of magnitude difference in the response to that? And it turns out it's a very subtle but very important point that will teach us a lot about why enzymes are as good as they are. Enzymes aren't just provide us things that allow us to do reactions, but the nature of the binding itself also drives reactions forward and makes them faster. So we'll look at the idea of proteins folding and binding, and why does it accelerate reactions so much, and why do we need it so bad? We'll look at that next time from the perspective of thermodynamics. We'll look at a few more things. All right, so one more lecture of enzymes, and then for our last lecture on next Tuesday.
We don't have that.
Oh, is that right?
Yes.
So-
Tuesday, the reading day?
Yeah.